Hey everyone, and welcome to this explainer. Today, we're going on a trip deep into the mechanical heart of industry. We want to understand exactly how massive industrial machines transmit immense power without, completely tearing themselves apart. We're looking at the literal backbone of power transmission, advanced shaft, key, and coupling design. Let's get into it. Okay, let's dive right in. The source material kicks off with this quote, and honestly, it sets the stakes perfectly. Because it turns out, stepping out of theoretical physics and into real-world industry is a total battlefield. If engineers don't understand how these extreme forces interact with imperfect steel at high speeds, well, their designs just become really expensive shrapnel. To navigate all this, here is our master blueprint for today. We'll be hitting 1. The anatomy of the power shaft. 2. Metallurgical selection and alloys. 3. Thread analysis and predicting brakes. 4. Enforcing strict rigidity boundaries. 5. Anchoring and permanent connections. And finally, 6. The master assembly.
All right, section 1, anatomy of the power shaft. We need to define the shape.
Now, what's really interesting here is that power transmission shafts, they're almost never just simple straight rods. Just look at the architecture. It's a stepped shaft, and it's engineered with its absolute maximum diameter right in the middle, tapering down toward the ends where the bearings mount. And these steps aren't just there to look good. They provide physical mounting shoulders. Those shoulders let us precisely locate gears and pulleys, and they secure them against axial thrust. And hey, notice those tiny rounded internal corners at every step? Those are called fillets. They are absolutely mandatory to minimize stress concentrations. A sharp corner on a spinning shaft is essentially a pre-cut fracture point just waiting to snap. Moving to section 2, metallurgical selection and alloys. Choosing the right metal. So the sources make a great point here. Not all steel is created equal. On one side, we have ordinary machinery steels. Your standard medium to high carbon steels like 30C8 or 40C8. These are incredibly common, very cost-effective, and they're actually manufactured in standard millimeter increments, like 20, 25, or 30 millimeters, just to keep machining costs down. But on the other side, when operational loads become truly extreme, engineers bring in the heavy hitters, high-performance alloy steels packed with chromium, molybdenum, and nickel. When experts specify a complex alloy like 40Ni 10Cr3Mo6, they aren't just buying metal, they're essentially buying insurance against impact fatigue.
Section 3 now. Thread analysis and predicting brakes. It's time to map those invisible forces.
Okay, this is our absolute baseline mathematical rule, the fundamental stress axiom. Stress literally equals force divided by area. This one simple equation dictates how external forces translate into internal pressure within our chosen metal. And our main goal as designers is to figure out the exact minimum safe diameter required to prevent the metal from yielding under all that stress. And this brilliantly illustrates what we call the power trio. Basically, there are exactly 3 ways a force can attack our shaft. First, axial load. Those are tensile forces physically pulling the shaft right along its center line. Second, the bending moment. Transverse forces from heavy gears or pulleys that cause the shaft to physically bow in the middle. And third, the torsional moment, that pure twisting force that actually transmits rotational mechanical power from one end to the other. Honestly, every shattered shaft you will ever see was brought down by one of these 3 forces. Now, you might be wondering, it's easy enough to calculate just a twist or just a bend, right? But real machines, they don't play nice. Bending and torsion attack at the exact same time. So how does the metal actually decide when to snap under this complex combined assault? Which brings us to predicting the break. Look, materials have finite patience. When combined loads hit our shaft, they create these complex principal stresses that simple formulas just cannot evaluate on their own. To predict when the metal will violently tear apart, we absolutely have to choose a governing failure theory, and that choice is based strictly on the physical metallurgy of the shaft itself. It's actually kind of amazing. We basically have to force 2 major mathematical theories into a head-to-head showdown. On the left, we've got Rankin's maximum principal stress theory. That one is highly accurate, but specifically for brittle materials like cast iron. But over on the right, we have Tresca's maximum shear stress theory. In actual industrial practice, transmission shafts are virtually always machined from ductile steel. Because of this, the industry universally relies on Tresca's theory. Under Tresca, we predict failure based on the maximum shear limit, which means the permissible shear stress for our metal is exactly half of its tensile yield strength. Listen, if you use Rankin's theory for a steel shaft, it'll shear apart in the real world, while your math insists it should be perfectly safe.
All right, Section 4, enforcing strict rigidity boundaries. We have to shift from preventing a catastrophic break to preventing operational dysfunction.
Check out the rigidity axiom. The source gives us this incredible piece of expert insight. A shaft that bends but doesn't break is still a failed shaft. Why? Because if your shaft sags or bows even a fraction of a millimeter too much, the hydrodynamic bearing supporting it will literally starve of oil, and the gears attached to it, they'll misalign and grind themselves into fine metal dust. So strength keeps the metal in one piece, for sure, but rigidity keeps the machine actually working.
So the really crucial point here is that engineers have to legally restrict the amount of twist and bend they permit. Take torsional limits, the angle of twist. This is incredibly vital for timing mechanisms. As for lateral limits, the actual bowing of the shaft, deflection is strictly bounded relative to the span length between the bearings. If you try to stretch that span length just to make assembling the machine a bit easier, your deflection grows exponentially. The secret to a truly rigid machine: keep your bearings tight and your spans short.
Moving on to Section 5, anchoring and permanent connections, how we lock these components in place.
Notice that glowing rectangular piece of metal on the screen? That is the key. It's such a simple, heavily standardized little machine element that just slides into a groove between the shaft and the gear hub. Honestly, the key is usually the absolute cheapest part of the entire assembly, but it is the critical gatekeeper of the whole system's torque. It completely prevents any slipping between the components. But be warned, if you cut the keyway poorly, you create a massive stress concentration that will easily snap your expensive shaft. And because that key takes the brunt of the shearing force of the torque, engineers use what's known as the 1.57D rule to size it. By making the length of the key exactly 1.57 times the diameter of the shaft, you ensure that the key will fail by shearing way before the shaft itself twists apart. It is absolute design genius. You're intentionally designing a mechanical fuse. I mean, it makes perfect sense. You'd much rather replace a sheared $10 key than try to extract a fractured, seized $10,000 shaft from a heavy-duty gearbox.
But what if we need to permanently connect two completely separate machine units, like, say, an electric motor to a massive water pump? That's where couplings come in. Rigid flange couplings bolt shafts together, sure, but they demand absolute perfect collinear alignment. And the problem is, perfect alignment in the physical world is a total myth. Thermal expansion and settling foundations practically guarantee your axes will eventually offset. That is exactly why the industry relies heavily on flexible bushed pin couplings. They use these rubber or leather bushes around the pins to absorb shock loads and allow for a tiny, like 0.5-degree misalignment. Believe it or not, that tiny bit of flexibility is often the only thing preventing high-frequency vibrations from literally shattering the concrete foundation the machine sits on.
Let's move to Section 6 and see how this builds. The final master assembly. Theory becomes reality. So let's bring our entire blueprint together. Step 1, we use stepped geometry to minimize stress and correctly position our gears. Step 2, we rely on Tresca's theory to dictate the absolute minimum safe diameter of our ductile alloy. Step 3, we enforce strict rigidity limits to guarantee our gears and bearings survive operation. And Step 4, we utilize mechanical fuses, like the key, combined with flexible couplings to unite the entire system together safely. As you can see, every single variable we calculated perfectly supports the next in the chain. You know, it's easy to look at a stunning assembly like this and just see a bunch of disconnected formulas and metal parts. But once you truly understand the source material, you see a living, breathing system. True master design is simply the intersection of strength, rigidity, and integration. When you perfectly balance those three things, theory seamlessly becomes reality, and you have built the true backbone of power.
Wow, we have covered a massive amount of ground today in this explainer, essentially turning invisible forces into perfectly machined steel. The rules of power transmission are absolute, and they govern literally everything from your car's gearbox all the way to the turbines powering your city. The math is sound, and the blueprint is perfect. The only question left is, how will you apply these engineering laws to ensure your next design survives the brutal reality of the physical world? Thanks so much for joining me today, and keep looking closely at the machines around you.